All right. Sorry about the delay, everybody. We're just having some minor technical difficulties, but welcome. Good morning. My name is Felipe. I'm a creative director here at MakerBot. Live from New York City again. This is episode 5 of our MakerBot chats. It's great to see you guys out there. Also, as you guys know, Alejandra will be, in the back in the production part of this whole episode. Uh, Collecting all of your questions, all of the feedback that you guys might have. And yeah, it's exciting to join you guys again. And let's get started. So I have a few new parts for us to talk about this week. I tried different setups. I wanted to show, and I did this in Instagram. So for those of you guys who follow us on Instagram, you will see that grid array where I was showing some of the parts that I will be talking about today. It's going to be hard, and I'm trying to find like what's the best way to do the setup here because it's getting a little bit old just to see here the living room. But I'll bring some of the parts over so that we can start the conversation. And sorry, it's just with this. Sorry. With the number of setups that I got here and just trying to make everything work out of the living room, it's kind of complicated. But today's conversation is about part tolerances, specifically for assemblies and with different systems. What should we expect when 3D printing a part? What are the best practices? What are the ballpark measurements that you should have into consideration when giving yourself uh, tolerances for assemblies for specific parts? I have a rundown of parts starting with this very it's older project, right? I wanted to talk about this for a while. It's a drone that we designed using the Replicator Plus series. As you can see, it's printed in multiple colors, and it also actually works, right? So it does have all of the components, all of the brushless motors. It even has tiny camera out front. It was a really exciting project back then. But as we were building it, right, we came into some of the issues with heatless, let's say, 3D printing, which are the fact that you need to give yourself a little bit of a wider and bigger tolerances just to make sure that everything is going to fit into place, right? This assembly, it's not super complex. It's made out of the main body, the cap for the main body, and then also smaller caps that keep the motors in place. You can see that I've already lost one here, actually two of them. Maybe I dropped it in that way here. Uh, but overall, right, as I was building this, I had to consider and give myself about 200 microns worth of an offset to make sure that all of the parts would fit. You can see that I was also a little bit hindered by not having soluble supports because I didn't have Method back when I was designing this. And because I didn't have soluble supports, I didn't really want to use breakaway supports because sometimes that can damage the underside of your parts. It can be very hard to remove them depending on the part that you're using. And especially for more advanced materials like ABS, breakaway supports are hard, which is why soluble supports like SR30, which is what you have with the method, it's just way easier to use. But in any case, specifically about the housing, here you can see all of these little protrusions, right, that are going to guide my cap in place. I gave myself a good 200 microns of offset just to make sure that the part would nest nicely and smoothly. It would be a clamping assembly, super straightforward. And then also here, for some of the parts that I wanted to create with some, action there, right? This part is basically going to control the on and off switch of the drone. It's right inside, and I'll show you here, right here. So you can see that pink switch. Oh, here we go. The pink switch right there is being controlled by this lever action. So I just left myself a good 1 millimeter offset, and that was enough to give me, this flexing action without sacrificing the integrity of the material. It was printed in tough material, so tough is a little bit more flexible than PLA, also even more so than ABS. It's kind of chewy in a way. So great for some of these action elements where you have either a leading hinge or a part that's going to move a little bit, right? It's not going to be completely flexible like what we've seen before with CEFs or even TPU, right? Which are completely, meant to be deformed. This is just going to give a little bit, right? But if I force it for more than a few cycles, it can be complex to keep the integrity of the part in check. Now, when printed with the more basic systems, right? One of the issues that you will also have is part orientation. The way that you print your part, whether you print it horizontally, well, actually vertically like that, or horizontally, will affect how round some of your holes are. Why? Because many of the more basic printers that don't have a super sturdy frame will flex a little bit, will flex enough, deforming your part. So if you can imagine, like, it's going to be hard for me to show you in this one, but some of the circles behave more like ellipses because the part, well, actually the frame of the printer flexes just a little bit. It's not a lot for parts that don't require higher degrees of precision, but it's a lot for something like these where the part needs to be just spot on, up to spec. You need to make sure that these circles are going to be entirely round so that either a nut will fit in place or the bolt will fall through if you have specific anchor points that they are going to just match the dimension that you have. And with method, well, you can actually control that, right? Regardless of the part and the way that you orient the part. Even then, and I have a good example here of something that I'm working on right now. Let's see. Here we go. Even then, it's a good practice overall to have some of the more critical elements like this circle in this propeller. So this is a propeller that I'm printing here. It's an experiment. We'll talk about it in a few weeks, and it's exciting, right? But I cannot talk a lot about it. But anyways, this propeller, I could print it in many ways, right? I could orient it like this. I could orient it vertically. Overall, with circles, I would say a good rule of thumb is to have them parallel to the build plate, right? So facing, basically the normal facing up. Why? Because that'll actually guarantee that you have as little deflection. And also, not only that, but with a circle, more often than not, you will require, say, if I have to rotate this part here in X, right? If I wanted to print it this way, I will need supports all the way inside of the circle, inside of the cylinder, even in these little side holes that are basically just for mounting purposes there. So it will create a longer print time wise. It will consume more material, and it's just yeah, the precision with circles when printing vertical versus horizontal can change a little bit. Not so much in method, but for sure in other systems where you're relying more on wider tolerances. So general rule of thumb: print your circles oriented vertically. And as I keep going, you do let me know if you have any questions. Alejandro is collecting. I see some of the questions already coming in. But anyways, pointing your circles straight up just to make sure that they are actually going to be as circular as possible. And even then, having a system that will deliver those circles is really important. So in the case of method, you do have two massive pillars. So let me switch back here to my main camera, right? The sides of the printer. So these two components right here, this is basically an aluminum extrusion that runs all the way up from the base to the top. The extrusion itself is a good like 4.5 inches. And it guarantees that the printer doesn't flex at all when you're printing, right? So as you can imagine with such a system, let's see if I can move the camera a little bit here. Here we go. So you can imagine how, as the gantry, and the gantry is going to be this part that will host. Sorry, I'm actually holding the computer right here. So the gantry is this massive part that holds both extruders in place. As the gantry moves along, this weight will want to move and jitter the printer quite a bit. If you don't have something holding that part together, so these two pieces run, you can see actually the seam right here. Yeah, there we go. Right here, running all the way up here. So it's a very sizable aluminum extrusion, right? That guarantees that as the gantry moves, as the printer runs back and forth, you will not have that motion translated in any type of flexing within the printer. What that means is that you're actually guaranteeing that the nozzle stays put and doesn't flex even a little bit in any of the axes, right? So you get that guaranteed part accuracy just by the fact that, well, basically the system is pretty sturdy. If you imagine some of the more basic printers that have even in the Rep 2, where we had just an aluminum rod running up the system and maybe some side panels, we see other printers that have basically polycarbonate panels on the side. You will not see the printer flexing, like that, but it's going to move enough in an unnoticeable way for the eye, but enough for the part to stop matching, especially when printing, tiny circles, tiny features that you really, really want to make sure that are just cylindrical across the whole part. So basically, what happens with this part, right? And in this case, I had no choice. So my rule sort of breaks there because the part needed to have and orientation anyways, and because of this, the fact that these circles and these circles are not parallel to one another, no matter how I orient my part, I am going to have a challenge facing all of the circles in a single direction, right? So in this case, this part was printed like so. It didn't require that many supports, and because of the fact that method controls fairly well the temperature, or consistently the temperature across all of layers, I got perfect cylinders throughout the whole part and in multiple phases that were not affected by either motions of the printer or temperature changes, because of the fact that the whole chamber was controlled. I have another interesting part here that I'm working on. This is it's kind of a personal project right here, but it's going to be a bicycle rack. I'm printing it in it's very tight actually. Yeah, there we go. So I'm printing it in multiple pieces. Let me just check one. Okay, so I see one of the questions. What's the difference between dimensional accuracy and dimensional uniformity? Well, overall, I would say that the accuracy refers to a specific point. The uniformity means like constantly you get the same performance in the printed object, right? So it's not going to change depending on whether you're on layer 1 or you're in layer 10,000. That does happen with some of the printers that use a build plate, because if you're right up against the build plate, you have very good accuracy, right? The plastic is happy and hot and warm, and it behaves as you would expect it to. However, as you get away from that build plate, right, as the build plate recedes from the extruder, then you start losing some of the benefit of having heated build plate. With a chamber, the dimensions stay put uniformly throughout the whole, with a heated chamber, right, throughout the whole print, because you're not controlling just a single layer or just a few layers that are right up against the build plate. You're controlling the whole print as it goes through, as it runs through the system. So going back to this example, so in here I was printing this dovetail, and let's see, I don't think I have the specific Zoom version of it. It's basically, a dovetail. I wanted it just to be a simple jigsaw sort of assembly right here. I will have, this is just the next segment over of this rack. It's going to be way bigger. It's about 18 inches across, so I had to split it into multiple parts. And I wanted to make sure that it would be sturdy, right? It would just stay in place. So what I did here is basically give myself about 100 microns. You can see how tight it is, so that the parts will slide together, and as they do so, they become really, really, really tightly packed together, right? Depending on the type of assembly that you're trying to achieve, you will have to change the tolerances that you are playing with. In this case, I used 100 microns. 100 microns, it's almost like a press fit assembly. That means that once it's in place, if I run it all the way through, it's going to be fairly hard. Oh, there we go. It's almost there. Fairly hard for me to take it out. If you go anywhere below 100 microns of an offset between the two parts, so you can see it right there, it's really, there we go, really, really tight, right? If I go beyond, well, actually below those 100 microns, the part, once I set it, it's almost going to be set it and forget it. It's just stuck there, right? From now on, those two parts are going to behave as a single one. Why? Because the material friction and the friction between the walls, it's not only the tolerance, but the friction increases between the two walls of the material, and basically locks the material in place. If you wanted to have something, with a little bit more give, even with method, you could have a bigger tolerance. So kind of what I was showing here with the drone, about 200 microns would do the trick. If you have a more basic system, I would give myself like half a millimeter offset. I think it's great for looser fits or looser fitting parts. So that's kind of what happens with this toy assembly, right? So I just have half a millimeter there, half a millimeter up against the peg. That's going to, create my assembly. And it's super easy to rotate, it's super easy to play with. But the goal here was not necessarily to have something super tight, right? It was more just to have something that would fall in place and prevent the wheels from falling to some degree, right? You just saw that it actually did slide out. So it depends a lot on your system. Overall, with Method, you have two microns per millimeter of travel. That's kind of the claimed accuracy. If you have a system that just has the heated build plate, then that might change a little bit. Can shrinkage occur in 3D printed parts? The answer is yes, of course. If you have a 3D printed part, think about it, especially with thermoplastics, right? ABS, polycarbonate, PLA, tough materials, they are going to all have to change a little bit as they cool down, right? The part that, as the name suggests, a thermoplastic reacts to thermal changes. So if you cool down the part really fast, right? If you just extrude the filament out, and let's say that you're running it at 200 C and hit the build plate at 100 C, and then the ambient temperature at 25 C, then you can imagine how those very steep gradients are going to challenge the part, are going to challenge how the part actually behaves. And the part will sort of, contract really fast. I don't have a good example of that because, it's hard to do that with the method unless I disable the heated temperature, the heated build plate, the heated chamber. But overall, what happens is that the part will sort of shrink onto itself, and it'll create these divots, these deformities, especially on the outer walls, that are going to challenge your accuracy, your part fitting, and ultimately the way that the assembly behaves, right? That's also true for some of the printers that use the build plate, but it can be solved depending on how you orient the part. However, changing the part orientation can add other challenges. In this case, I printed these two parts vertically like that. If I was to print it, horizontally, so that, let's say, I don't have the need for a constant temperature throughout the whole chamber, it's closer to the build plate, and I want to make sure that stays put, then I would require supports in all of these divots. So this part is actually generated in Grasshopper, in Rhino, and this pattern is going to be a Voronoi pattern. So it's a kind of a cell, very kind of biological, organic looking pattern. So it's a lot of different polygons forming this. So all of these cavities will need supports once I print them sideways, right? It can be difficult. It definitely can be achieved, but I would say yes. Thermal expansion is an issue, and it's something that you have to consider. Using a fully controlled system, it tends to be way better than, here, let me bring this part, way better than just using a heated build plate. And as we were talking about, last time, it also changes a lot with the soluble supports and the type of supports that you're using. In this case, with polycarbonate, right? This white part is made out of polycarbonate. I think some of you guys may have seen it in the past, but the same issue is true, right? So I was trying to put, testing the orientation, always focusing on or trying to make sure that the cylinders are facing upwards. So cylinders align to the Z-axis in the printer, going upwards. And then, after that just comes in the supports where needed, right? So in this case, all of this empty space would have needed supports if I printed it against the build plate. If you have soluble supports, that's great, especially because in this case, I'm using SR30 supports, right? Which are going to behave in a very similar way than polycarbonate. If you have supports that are made out of a different material, then you can have also a challenge in the way that one material behaves versus the other one, right? You can have a material that actually wants to be cooler than the main material. So that can also challenge a little bit your printing process. Filament versus dimensional accuracy. I'm not sure I'm reading that question correctly, but overall, the materials, well, okay, I guess that the question goes to whether there are any changes on using, let's say ABS versus polycarbonate for material accuracy. It depends, right? With Method and with MakerBot, all of the materials that are going to be MakerBot materials are proved. They are thoroughly tested. I think that the benchmark right now, it's about close to 1,000 hours worth of printing. I would have to check that for you guys, but it's going to take a long time for a material to be validated as, actually I have ABS here, to be validated as a MakerBot material. And that means that any of these materials, ABS, ASA, SR30, PLA, TUF, are going to behave in an expected way, right? You will know the exact tolerances, and you can go to the site. I'll take you there in a second, but are going to behave. Just bringing the site real fast here. In an expected way all the time, right? They are going to be having matching dimensional accuracy, matching tolerances, and matching offsets, which is ultimately what you want, right? You want the part to behave in an expected way, so that it actually, let's jump right here, bringing my window. Give me 1 second. That the part is going to behave in an expected sort of way. So in this case, just going to the website, and if you go to materials, each of these materials, and we have quite a big list now, right? But each of these materials, if you click on them, let's go to the PETG material right here. We'll have the relevant data sheet right here where you can see the individual tolerances. You will have also the precision claims within that sheet, and you will be able to go through, what are the specific technical specifications for said material, right? Overall, quick answer, yes. If it's a MakerBot material, the tolerances, the precision will stay there, will stay put, and will match what you're expecting. If it's not, if it's a material that you're side loading, if it's a material that you're using through our MakerBot Labs platform, then it depends. Some of them have been proven, and some of them we actually have a Thingiverse group that is continually updated with the best practices and best the best settings to print with any specific material. So visit that, and you will be getting the best results. But overall, MakerBot materials and then labs materials that have been proven will have certainly similar performances. As I said before, we're still running that promo. If you guys want to check it out, it's a crazy thing. A method right now with I think it starts with 10 different materials, I want to say, plus the labs, which labs just makes you go and have a million more. But it's starting at $3,500. It's a really darn good time to get one. It's kind of crazy, when I first heard about the promo. Just throwing that out there, if you guys are interested, it's a pretty good time to get it. Method X, it's a beast. It has all of the materials, all of the possibilities. It's just awesome to work with and to have around. But in any case, that sort of does it for me. I'm going to just have a last check to see if there are any more questions. If not, let me know in the comment section. You can always reach out to us, whether in hello@MakerBot, that's our general question email, or you can also reach directly to me to felipe@makerbot.com. I am receiving all of your emails. I actually have to reply to them shortly after this, I hope. But yeah, it's great to hear that you guys are liking this frame or actually setting. I will try a few different options for the next one, maybe changing the views and changing some of the way that we show you the parts. And we have a few announcements, quite interesting ones, coming in the following weeks. So make sure to subscribe to our channel, either hitting that notifications icon in YouTube or going to our social media accounts @MakerBot, both in Instagram and Twitter. And until next time, thanks a lot for joining, and have a good day, rest of your day. Thank you.